Hey everybody, Dr. A here, and in this video we're going to be providing a little bit of background information and exploring some examples of evaluating partial derivatives. So let's go ahead and get started. A partial derivative is a derivative or a rate of change for a dependent variable with respect to an independent variable. Now, that seems like a very similar definition as an ordinary derivative, okay? But what's the difference when we have a partial derivative compared to an ordinary derivative? Well, this difference comes into play based on the type of function you have. So more specifically, when we have a multivariable function, which is a function where we have multiple independent variables, that's when this idea of partial derivatives comes into play, okay? Now, we see these applications often in physics, engineering, differential equations applications, and multivariable calculus. So again, think of a function with multiple independent variables, right? If we have a single independent variable, then it just goes back to basic calculus 1 and calculus 2, right? But what if you have a function where you have one dependent variable and more than one independent variable, and you want to find these first order partial derivatives, okay? So how does that work? Well, let's go to the next sentence here. Generally, for continuous or smooth multivariable functions, the number of first order partial derivatives equals the number of independent variables. Now, what do we do with the other variables that we are not differentiating with respect to? So when differentiating with respect to one of the independent variables, the other variables are going to be treated as constants, okay? So that's kind of the background information of that. So how can we write this kind of mathematically? I'm going to say for a multivariable function, z as a function of maybe x1, x2, x sub I, all the way to x sub n, then the first order partial derivative, first order partial derivatives are the following: dz dx1, comma, dz dx2, comma, comma, dz dxi, comma, all the way to dz dx sub n. Now you notice I drew these d's a little different, right? So an ordinary derivative will write a d in the normal fashion. Well, when we have a partial derivative, just to distinguish a partial derivative from an ordinary derivative, we kind of give the d symbol this kind of curly shape here, okay? So for example, this term here, this is the partial derivative of the dependent variable z with respect to the first independent variable x1. And this second term is the partial derivative of z with respect to the second variable x2, so on and so forth, okay? So this goes back to this sentence. Generally, for continuous or smooth functions, the number of these first order partial derivatives is going to equal the number of independent variables we have in that multivariable function, okay? So let's jump into some numerical examples to practice this, all right? So here we're given the following. We're being asked to evaluate the first order partial derivatives for each function, okay? So let's look at function A right here. We have f of xy equals x squared plus y squared. So this is an example of like a paraboloid. It's like a three-dimensional parabola, okay, or a smooth parabolic surface, all right? The independent variables are x and y, okay, and the dependent variable is f. So under solution here, I'm going to write solution right underneath it. The first order, there's going to be two first order partial derivatives. The first one is going to be df dx, okay? And so again, we're differentiating with respect to x, and we're going to treat the other variable, in this case y, as a constant. So this first order partial is going to be 2x, okay? What about the other first order partial, df dy? Well, here we're going to treat x as a constant, and we're going to differentiate with respect to y. So this one will just be 2y, okay? That one is pretty straightforward. Let's look at this second example here. In this second example, example B, we have z equals sine of x plus cosine of y. So here we've got these two independent variables, and z is our dependent variable. So here under solution, I'm going to say dz dx, okay? So I'm differentiating with respect to the variable x here. And so what's the derivative of sine? Well, that's just going to be cosine of x, okay? Now, what about the cosine y term? Well, when we differentiate with respect to x, the y term is going to be treated as a constant. So what happens if we take the derivative of a constant? Well, it goes to 0. We saw that in the previous example here. And so similarly, we can get dz dy is equal to what? Well, pause the video if you want to try to figure it out yourself, because I'm about to tell you the answer. We're going to get negative sine of y, okay? And the reason is because in this partial derivative, the x term is going to be a constant, so it zeroes out. When you try to take a derivative of a constant, it's 0. And cosine of y, derivative of cosine, is negative sine, and of course, we keep that variable y there, okay? Let's do another example here, okay? Here we've got a function with 3 independent variables, x, y, and z. So here, how many partial derivatives, first order partial derivatives, are we going to have? Well, we're going to have 3 first order partial derivatives, okay, because this is still a smooth or continuous function, okay? Now, this is what we would sometimes call a hyperfunction, because this has 3 independent variables and 1 dependent variable, so we can't really visualize this with a human brain. So we sometimes collectively call these hyperfunctions when we have more than 2 more than 2 independent variables. Okay, so let's take all 3 of these first order partial derivatives. We're going to get df dx is just going to be equal to 2x. And again, the y and z terms are going to be treated as constants, so they zero themselves out, okay? We're going to get df dy is going to be equal to negative 6y. And again, the reason is because we're differentiating with respect to y, so the x term and the z terms are going to go to 0 when we take those first order partial derivatives. And then finally, we'll get df dz is equal to 4z. Again, the x and y terms here zero themselves out when we take that partial derivative with respect to z, leaving a 4z, okay? Let's do one more example. This one looks a little bit more complicated. We have 2 independent variables, x and y, and so we've got sine of x times y plus cosine of x times y, okay? So how do we perform these 2 first order partial derivatives? Well, first, there's 2 of them, 2 first order partials, one with respect to x and one with respect to y. Let's do df dx first, okay? So here, y is going to be treated as a constant, okay? And x is the variable, all right? So what's the derivative of sine? Well, first derivative of sine is going to be cosine. So this is going to be cosine of x times y. But remember, you've got the chain rule that kind of comes into play here, because y is treated as the constant right now, so that y is going to come out in front. So really, that first is that term is going to be y times cosine of xy, okay? What about the second term? We're not done yet. We got to say plus derivative of cosine is negative sine. So really that's going to be plus a negative y times sine of xy. So if we were to kind of rewrite this a little bit more compact, that's going to be y cosine xy minus y sine of x times y. And if you want to, you could factor out a y there, and you could get y times the quantity of cosine xy minus sine of xy, if you want to show that, factored out to some extent. Okay. Now, what if I want the first order partial derivative with respect to the y variable now? Well, I follow a similar kind of process, except x is going to be your constant here, okay? And again, you're differentiating with respect to y. So that first term is going to be x times cosine of x times y, and then that second term is going to be minus x times the sine of x times y. And of course, if you want to factor that out, you can get x times the quantity cosine xy minus sine of xy. Okay, so the moral of this story is, when you're computing partial derivatives with respect to one variable, the other independent variable or variables are all going to be treated as constants, so just like regular numbers, okay? And you need to manage them as such. The other thing to keep in mind is all of your basic differentiation rules that we learned maybe from Calculus 1 are still going to be valid when you're finding first order partial derivatives. Okay, so that concludes this background video with a couple of small examples of partial derivatives. If you found this helpful, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.